Normal force. When objects are in contact with each other, each object exerts a contact force on the other object. What does Newton's third law tell us about these forces? It tells us that they are equal in magnitude and opposite in direction. This book and desk are in contact with each other, and they are each exerting a force on the other. What is the force that the book is exerting on the desk? When we talked about the gravitational force, we saw that the gravitational force exerted by the Earth on an object near its surface can be written as F sub g equals m times g. We also saw that this is equal to the weight of the object. So weight can be thought of as a force. The downward force that the book is exerting on the desk is the weight of the book. The force that the desk exerts on the book is equal in magnitude and opposite in direction. We call this the normal force from the desk. This force is called the normal force because if you draw a line perpendicular to a surface, that line is called the normal to that surface. The normal force is actually just one component of the force that a surface exerts on an object with which it is in contact. It's the component of the force that's perpendicular to the surface. The magnitude of the normal force can give us an idea of how hard two objects are pressing against each other. In our previous example of the book on the desk, the magnitude of the normal force from the desk to the book was equal to the magnitude of the weight of the book. But the magnitude of the normal force from a surface to an object is not always equal to the weight of the object. For example, let's say the magnitude of the weight of our book is 13 newtons. Then let's say I'm pressing straight downward on the book with a force of magnitude 9 newtons. That isn't enough force to push the book through the desk, so the book is still sitting stationary on the desk. Since the book is sitting stationary on the desk, it's not accelerating. What does Newton's second law then suggest about the net force on the book? The net force on the book must be zero if the book is not accelerating. In order for the net force on the book to be zero, there must be an upward force that cancels out these two downward forces. The only upward force on the book is the normal force, so the normal force is equal in magnitude to the sum of these forces. In another example, what if I tied a rope around the book and it pulled upward, applying an upward force of magnitude 9 newtons? This is not enough force to lift the book, so it stays still on the table. Again, the book is not accelerating, and so according to Newton's second law, the net force on it must be zero. In this case, the force I'm applying to it is upward in the same direction as the normal force. In order to get the forces to balance this time, the weight of the book must be equal in magnitude to the sum of the magnitudes of the upward forces. This means that the magnitude of the normal force must be equal to the magnitude of the weight of the book minus the magnitude of my pulling force. This gives us 4 newtons for the magnitude of the normal force. Since the magnitude of the normal force is not always equal to the weight of the object, you want to make sure to consider all forces in the direction you're interested in when looking for the magnitude of the normal force.